Lecture 26 covers sections 8.2 through 8.3. At the end of today's lecture, you should be able to construct and apply the constitutive equations for an RC circuit, that is a circuit that has resistor and capacitor, and an RL circuit, that is a circuit that has a resistor and inductor, to determine both the natural and forced responses of the circuit. To begin, let's consider the following RC circuit. We have a voltage source that is applying a potential to a resistor and capacitor, which are existing in a series configuration. The current running through our capacitor is equal to our capacitance times the time rate of change of our voltage potential across, and this current is also running through our resistor. For us to analyze this circuit, we are going to construct a KVL loop around it, where we have our source voltage being equal to our voltage drop across our resistor plus our voltage potential across our capacitor. That is, VOC is going to be equal to I of t RT plus V of t, where I of t is running through our resistor, R sub t, and V of t is our voltage potential across our capacitor. Recalling that our current running through our resistor and capacitor is expressed as our capacitance times the time rate of change of our voltage, we can say VOC is equal to our capacitance times the time rate of change of voltage times our resistance plus the voltage potential existing across our capacitor. Or if we express this in terms of our highest derivative, d of v of t dt plus v of t per RTC is equal to VOC per RTC. Now, before we solve that equation, let's look at an RL circuit, where we have a current source in a parallel configuration with a resistance, R of t, that is connected to an inductor in a parallel configuration as well, where V of t is our voltage potential across our inductor, and I of t is the current running through our inductor. Now recall our voltage potential across an inductor, V of t, is equal to our inductance times the time rate of change of current running through it. For us to analyze the behavior of the circuit, we want to apply KCL at our top node, such that we can determine the current entering and exiting our node. We have I sub SC entering our node, and then we have our current running through our resistor, which is expressed as our potential V of t per the resistance, R sub t, plus I of t, the current running through our inductor. If we recall our voltage potential across our inductor being L of di of t dt, we can say I sub SC is equal to L per R of t, di of t dt, plus I of t. Or if we express this in terms of our highest derivative, di of t dt plus R of t per L I of t is equal to R of t per L ISC. Now what we recognize is the solution to these following equations is one and the same, because we recognize that both our RC and RL circuits have a response in the form of a first order differential equation. That is, dx of t dt plus x of t per tau is equal to k. Our RC and RL circuit both take this form. Thus, if we can solve this particular differential equation, we have a response for both circuits. To do such, we introduce tau as a time constant, and k is just going to be a constant. Now, to solve this differential equation, we are going to use separation of variables. That is, we're going to say dx dt is equal to the quantity k times tau minus x per tau. Or we can say dx per x minus k of tau is equal to minus d of t per tau. Now we want to integrate with respect to each variable. So we're going to have the integral of 1 per the quantity x minus k of tau dx is equal to minus 1 per tau, the integral of dt. If we evaluate our indefinite integrals, we have the natural log of x minus k of tau is equal to minus t per tau plus c, where c is our constant of integration. Now to solve for x of t, we need to exponentiate. We are left with x of t is equal to k times tau plus a constant, e to minus t per tau. We recognize that k of tau is our steady state response. That is, there is no time dependence on the solution. And a e to minus t per tau is our transient response, a function of time. We notice this response is going to tend to 0 as time tends to infinity. Now to solve this, we need to apply an initial condition. Our initial condition within our system is x when t is equal to 0 is going to be equal to 0, such that x naught, our initial value, when t is equal to 0, is equal to k of tau plus ae to the 0. E to the 0 gives us a value of unity. Thus we can say a, our constant, is equal to x naught, our initial value, minus k of tau. Now, we can express our solution as follows. X of t is equal to k times tau, our forced response, plus x naught minus k of tau, e to minus t per tau, our natural response. As time tends to infinity, we should reach a steady state process. That is, as we have e to minus t per tau with t tending to infinity, this value will tend to 0, and x of infinity is going to be equal to k of tau. Thus, we have one unknown variable left within our system, our time constant, tau. We have to recall what other information we have about our system to solve this. And as t tends to infinity, we'd recognize that x of t would be equal to our steady state response, x infinity, plus x of naught minus x of infinity, e to minus t per tau. Thus, we can solve for tau based upon our steady state response of our system. If we differentiate x of t with respect to t, we can isolate our time constant tau. That is, we'd have dx of t dt would be equal to minus 1 per tau, x of naught minus x infinity, e to minus t per tau. At time t is equal to 0, we have our initial response. That is, dx of t dt at time t is equal to 0 should be equal to minus 1 per tau, x of 0 minus x infinite. That is, our e to minus t per tau goes to unity. If we rearrange for tau, we'd have tau would be equal to x of naught minus x infinite. That is, our initial condition minus our steady state condition per the time rate of change of x of t with respect to t, evaluated at time t is equal to 0. Thus, we have a solution for our time constant. If we go back to our RC circuit, x of t is going to be equal to our voltage as a function of time. Therefore, we'd have d of v of t dt plus v of t per RTC is equal to VOC per RTC. Now, if we compare this to the solution of our first order differential equation, we see that our time constant tau is equal to RTC. And our constant is simply equal to the right-hand side of our equation, VOC per RTC. Thus, our governing equation for our particular RC circuit described is given as V of t is equal to VOC plus a quantity V of 0 minus VOC e to minus t per RTC. Where in this particular configuration, our forced response is our open circuit voltage. That is, as time tends to infinity, our natural response would tend to 0. For an RL circuit, x of t would be equal to our current. And we'd have our differential equation described, di of t dt plus r of t per L times the quantity I of t is equal to RT per L ISC. We see by inspection or comparison, our time constant is equal to L per RT, and our constant K is equal to the right-hand side of our equation, R of t per L times ISC, our source current. Our governing equation becomes, for our given RL circuit, I of t is equal to ISC plus I naught minus ISC e to minus RT per L, where ISC is our forced response within our system, and the remainder is our natural response. We see that as time tends to infinity, our natural response is going to decay, and we're left with the forced response of our system.